Hello everyone, today we'll talk about dimension reduction. So, have you ever felt overwhelmed by datasets with too many columns to make sense of, or wondered how to simplify your data without losing important information? That's where dimension reduction comes to the rescue. Today, we'll talk about two powerful techniques identifying multicollinearity and applying principal component analysis or PCA. These are essential tools in your data science toolkit to make your data cleaner, simpler, and more effective for machine learning models. So let's dive in. So, dimension reduction is the key technique of data preprocessing used to address high dimensional datasets. It simplifies data without losing significant information, improving efficiency and interpretability. So, we will cover two major topics. First is of multicollinearity and other will be the PCA. So here we have the types of dimension reduction techniques. So here we have feature selection and feature extraction that involves selecting a subset of most important features from the dataset. It selects the subset which is the most important feature. So in feature extraction it creates a new features by transforming the original data. So methods like PCA falls under the categories as they construct new uncorrelated variables. So, so first talk about multicollinearity. This happens when two or more features in your datasets are highly correlated. Why is that a problem? Because it confuses models like linear regression, making predictions less reliable. So why detect multicollinearity? Multicollinearity inflates the variance of regression coefficient, making the model sensitive to small changes in data. It leads to unreliable statistical inferences and affects the model performance. So here are the methods to detect multicollinearity. So first is the correlation matrix. So it is a quick way to detect linear relationship between features. So um, a correlation should be greater than zero point 0.8 or should be smaller than minus zero point 0.8, and that is a right flag. Then we have the VIF that quantifies the level of multicollinearity, and VIF is equals to 1 by 1 minus r of whole square. So if EIF is greater than 5, then it indicates high multicollinearity. So then the condition number, so high condition number for matrix of feature suggests multicollinearity. So then we have steps to identify multicollinearity. So first we compute the correlation matrix. So start by calculating the pairwise correlation between all features. A value near 1 of minus 1 means strong correlation. Then we will check the variance with variance inflation factor. So VIF greater than 5 or sometimes 10 is a clear warning sign. So let's look at the code. So here's the code. In this, first we will import pandas as PD, then we will import numpy as np, and then we will import variance inflation factor. So next we will have a sample data set. Then we will do the correlation. Uh, then we'll make a correlation matrix, and then in step 2 there will be variance inflation factor. So let's print it. So here's the output with correlation matrix with feature 1, feature 2, feature 3 and feature 4, and here we have the variance inflation factors of all the 4 features. So here correlation matrix from our dataset. Notice how these two features have correlation. So um, so next, to summarize, using a correlation matrix help us to spot which features are highly correlated, while VFF qualifies their impact by addressing multicollinearity. We make our models more stable and interpretable. So now let's move on to the principal component analysis, that is the PCA. So PCA helps us reduce dimensions while keeping the most important information. Think of it as finding the essence of your data. So here's how you apply PCA step by step. So mathematical foundations of PCA. So first is the standardization. Then we have data is standardized to have zero mean unit variance because PCA is sensitive to scaling. Then we have covariance matrix that compute the covariance matrix to understand how features vary with respect to each other. Then we have the eigenvalues and eigenvectors, and then we have the principal components. So next we have the steps to apply PCA. So first is standardize your data. PCA is sensitive to scale, so standardizing ensures all the features. Then we will do compute principal components, that PCA creates new features called principal components that capture the most variance in your data. Then we have select step 3, that is select component, decide how many components to keep based on the explanation explained variance. Usually you want to retain 80 to 90% of the variance. In step 4, transform the data. Finally project your original data onto the selected components to reduce dimensions. So theory in PCA is the covariance matrix that measures how variables change together. We have eigenvalues define the directions of principal components, and after that we have eigenvectors that represent the amount of variance captured by each principal component. So now let's look at the code. So here's the code. So from sklearn we will first import PCA, then we'll import standard scalar, then we will import plot from matplotlib.plot, then we will have the sample data, and then we will do the standardized data. Then we will standardize the data, and then we will import the PCA, and visualize the PCA result with the PCA summary. So let's run it. So here is the output. So yeah, so the explained variance ratio tells us how much of each principal component contributes to the total variance. In this case, the first two components capture. So here, uh, we have feature 1, feature 2, feature 3, and feature 4, which are the principal components. So this is not so there you have it. We have learned how identify multicollinearity using correlation matrix and VIF, and how to apply PCA to simplify data sets. So dimension reduction, so here we have learned that dimension reduction is like decluttering your data. It helps you focus on what really matters. So here we have the outputs, that is explained variance, PCA plot, and a principal component. Thank you.